Let's talk about crystalline solids today, and we're going to talk about how ionic compounds do not exist as individual units containing one cation and one anion. In fact, they are more arranged in an orderly fashion. So I think there's a misconception out there that these crystals are going to be attracted to each other in such a way that they're kind of locked in. And the difference here is that they occur in 3 dimensions, or called unit cells. And usually they have a very flat surface and they make definitely some angles to each other. And this is the fact that they actually cleave along the plane. So if you take a look at some sort of solid and you're trying to figure out if the solid's going to have some sort of cleavage cutting through that plane, you're going to automatically know that there's some sort of angle that's kind of built in. Now, the arrangement of the atoms are really built around this idea that they're going to maximize coulombic forces. Basically, they want to minimize the attraction of repulsion, but they want to maximize the attraction between the like charges. So if you take Na plus, for example, and Cl minus, if you arrange them in a very specific case, what you're going to see is that they actually have a very strong attraction to the positive and negative. But when you arrange them, they have to be in such a way that they are aligned themselves in such a way that they're going to minimize that repulsion. And the way they arrange themselves are going to depend on the size of the cations and the anions. So if you have a very large atom and a very small atom, and when you align them in that lattice, where they call it, or unit cell, they're going to try to maximize and minimize those situations. And so let's take a look at sodium chloride as an example. In this case, sodium cation is surrounded by 6 chlorine anions. And if you take a look at this picture, it's pretty clear that, sodium has a pretty large, sodium has a pretty large radius, and they're kind of interlocked into this cube. And so what's really interesting about this, and I really like to, show these with models, is that the chlorine is surrounded by 6 sodium cations all around them. And so in this specific case, it's going to maximize that attraction and minimize. And that's the reason, minimize those repulsion forces. And that's the reason why you always have this specific kind of cube unit-like structure. And so if I ask you what is a coulombic force, what I'm really referring is that attraction that you have between those. Alright, so this is an example of a unit cell, and the unit cell is going to have these 4 corners around the cube. And so if you take a look at this, these blue dots here, what you'll see are these ions. And what these ions are going to do is that they're going to end up being in such a way that you're going to find them here in between the corners of these specific regions. And so what I really usually like to say is that when you're talking about these lattice points in these cubes, you're trying to find the maximum area. And so if I define a unit cell, I would define it along this area right here, and the ions would fit very nicely in between. Possible arrangements usually contain, it depends on how you arrange the ions, but if I take 8 corners and multiply by 1/8 of an anion, you're going to get approximately 1 ion per unit cell. And so there are a couple of arrangements. We don't really have to go too much in detail on this, but the idea is that you're going to end up getting these ions are going to be slotted in right between those cations. And this one actually has a little bit different structure. You have 8 corners times 1/8 of an atom plus 6 faces, and you end up with 4 ions of a unit cell. So let's talk a little bit about metallic solids. So when we're talking about bonding, it actually kind of breaks down into your secondary bondings, which are basically bonding are covalents. These are usually not enough to fill the octets. And the bonding usually occurs in metallic solids between these, what I call delocalized valence electrons. So electrons are kind of floating around the system. And what they usually do is that they allow those electrons to travel from one point to another. Now we take a look at things like iron and sodium, and we compare the melting points. The strength of the melting point of the bonds are much, much higher for metals. And the reason why is because if you take a look at iron, it has 8 electrons, and these electrons allow iron to really move through this. The iron allows the electrons to move through this valence shell, and because of that, the melting point for iron is actually very high. In fact, it's about 1538 degrees Celsius. So this stuff is really, really hot to melt compared to something like sodium, which is only 97.5. And so remember that in metallic bondings, it's not a covalent. It's more about trying to fill enough these octets, and these electrons kind of bounce off left and right. The most classic example is called the electron C model. And the electron C model is when you have an atom that floats around in between these cations. And because it floats around, the nuclei and inner core of these electrons are localized. Localized meaning that they're able to interact with the atom next to it. And so because of this, they're able to move around, and they have very interesting properties. The first one is that they're able to conduct electricity. Second one is able to conduct heat. The third one, they are malleable and ductile. And more importantly, they lack what they call directional bonding, which means that there really isn't like a set way of putting these bonds in place. And so if we're talking about metallic bonding, we're really not talking about sharing electrons. We're really talking about allowing electrons to move through. And that's the reason why you're getting some of these properties that come in. Alright, so a couple of terminologies that we want to get out of the way. So a solution by definition is a homogeneous mixture of two or more substances. We learned that already before when you mix them, but they're not chemically reacting. Solvent is when you got more of that one than the solution, and the solute is when you have less of that. So if I'm actually going to dissolve something, I want to be using obviously the solvent. And a classic solvent is going to be something like water. And an alloy is going to be a mix. It's a solid solution of a mix of two or more metals, and they're going to be including more metals or more than non-metals. And so you definitely have some of that part. So let's talk about the first example called an interstitial alloy. In this specific case, what you have is an atom that is small enough that can fit in between the spaces. Now, usually the radius is something small, so something like carbon is a great example of an interstitial alloy along with iron. And if you take a look at it, you actually create steel. And steel is a very, very great example of an interstitial alloy. It's used in many, many different applications. In buildings, it's used in, paper clips, anything that you can even think of that strengthens that metal together. Now, some properties of steel is that it basically has a lack of directional bonds. Similar to what I was talking about earlier, steel is a lot more rigid, it's less malleable, and definitely is less ductile than pure iron. And because of this, it forms very, very strong directional bonds. So if you have stronger directional bonds, what that means is that you're forming a strong connection between those atoms together. And by and large, steel is very good. It's usually greater than a pure iron, and it doesn't expand the lattice by much. And so if you take a look at the density equation, the choice of the matter of steel is a perfect example of a metal being used. Another example is called substitutional alloys, and this is when you get the radii of the solutes and the solvent atoms are similar, and brass is a classic example of a substitutional alloy. And the reason why is if you take a look at brass, you're putting in zinc and you're putting in copper. Most of the time, the density is going to lie in between one of these. And the radius for these are going to be similar, but they're not exactly identical. So if I want to replace one of the zincs for copper, what I do is I put them in there, and then I put them all in, and then they actually make those a lot better. So with that said, in summary, let's just kind of recap one more time. So bonding really breaks down into obviously your covalent and your ionic, but then there is this thing called metallic bonding as well. So make sure you understand metallic bonding, what it is, and how to draw these out. This is one of the most important parts of the exam, where you're taking a look at how atoms are being added in.